In the last class we had concluded that for the set of equations that I have given you, it is called the Lorenz equation. The origin will be a equilibrium point, the only equilibrium point before the value of r is equal to 1. Okay. After that, as the parameter r is changed through the value of 1, you have that particular equilibrium point becoming unstable, while two other equilibrium points then appear and become stable, fine. And then as you change r further, then you would see that the real part of the eigen values of those two equilibrium points which were having complex conjugate eigen values, that means they were having inward spiraling orbits, there the real part would slowly go towards 0 and finally at some parameter value it will cross 0, which means that they will also become unstable. So, we run into a situation where the failure at origin was throughout unstable after r is equal to 1, and the other two guys they also became unstable. What happens then? So, let us see how the orbits look like all through this sequence of events as the parameter is changed, and I will use a program that is a ready made program. You can easily do this by MATLAB coding. That is exactly why I asked you to do it. So, first let us start with a parameter value something like 0.8. Here is r is 0.8. Here it writes s, but we have written sigma, and it is b is 8 by 3, which is 2.67. Okay. So, if I now start the orbit simulation, you see it starts from this point and it goes to 0. Okay. Start from any other initial condition, it will also go to 0, and you can see that it is going to 0 act through a eigenvector, one of the stable eigenvectors. Now, let us increase the parameter beyond 1, while from theory we expect that this fellow here, the origin fellow, will become unstable and something else will become stable. Let us see if that happens. Let us increase it to say 1.8, okay, and let us increase the time. You can see that it was coming here, but it is going away. You can see, if you see it happening, but then it is going away. It is going away somewhere. If you increase the parameter further, say 10, now it will be clearer how it is going away. Can you see that now here there was one fellow that has become unstable, but now you can see a clear spiraling orbit spiraling inwards towards this, and do you see that the spiral is happening in a plane, right? It is this plane that I was talking about. How do you obtain this plane? As I told you, you have to obtain you can easily obtain the location of this equilibrium point. At that equilibrium point, you have to evaluate the Jacobian matrix, obtain the eigenvalues. Now, there will be one real eigenvalue and two complex conjugate. You can by looking at it, you know that the real eigenvalue is directed something like this, okay, and the complex conjugate eigenvalue associated with it, there is the eigen plane, and you can see that eigen plane, right? You can see that eigen plane here, and that eigen plane is to be obtained by taking the real part of that eigenvector and the imaginary part eigenvector, both real vectors. The plane passing through these two vectors is the plane here. So, you can analytically calculate this plane, but nevertheless the point is that here we have starting point is here and it is going through all sorts of things, and finally it is homing onto the equilibrium point. But you have also noticed from analysis that there should be two of them. So let us try to do that by doing a, it was the starting point was here 15, 10 and 40. Let us start from minus 15, 10 and 40. It was a symmetrically placed location, fine. So let us recalculate it. Okay. So you this fellow starts from the right hand side, and it goes and it converges onto this one. This fellow starts from here and it goes and converges onto this one. Happy? You can see the two planes now. There are two equilibria, the other fellow is unstable, and these two equilibria are now forming a plane, and along the along a line which is almost orthogonal to it, there is the stable eigenvector, and these planes are also stable eigenplanes, right, at this parameter value. Clear? Let us increase further. What do you expect? As you increase the parameter further, the eigenvalue, its real component will become, it will slowly become closer to 0. Suppose I do not go to the positive side, but it becomes closer to 0. What do you anticipate to happen here? Physically? No. What does the real part give? Real part gives e to the power sigma t. Yes, it will come in very slowly. Okay. The rate at which it is coming in will slow down, and therefore it will have very long going spiral. Let us see. Let us increase it to say 20, and see what happens. See, if you run it slowly, notice how it is going. Still it is homing into the equilibrium, right, both of them. Okay. So one from this initial condition, another from that initial condition, but you can clearly see the planes. Now let us increase the parameter more, and let us run it again. So if you run it now, it will become even slower in going down, right? The rate is slowing down. So let us stop it, no problem. Okay, now increase it further. Now I am slowly increasing it, not very fast though. 23. Quite slow, right? And we can anticipate that at 24 something will change. I am changing it here. Oops. See, they have become unstable, right? They are going out. Let us execute it a little slowly so that you can see the evolution. Okay, they are going out slowly though. Fine. If they are going out, the natural question is, where do they go? Where do they go? See, they are spiraling out. If you stop at this time 10 seconds, then they will stop here. This fellow has gone only this much, and that fellow has gone only that much. But you can anticipate that if you run it for a longer time, then this plane will intersect with that plane somewhere. So, this orbit will run into that orbit and that orbit will run into this orbit. Okay. Now, if I increase it the time of computation to a longer time, I'll run it faster, else it will not be able to follow. See, they are going out as anticipated from theory, but then something that cannot normally be anticipated from theory happens, right. Do you see the movement is visible properly? This is called chaos. Okay. So, it is not a very difficult to understand thing, it is reasonably simple state of affairs. Now, while this fellow goes on, let me tell you how this was first discovered. It was actually a model of the weather. Actually, in the there are a large number of people who try to model the atmospheric circulations, and from there they try to predict what will be the behavior, or they also try to predict the weather. For example, you may have heard that the weather prediction business in India requires a supercomputer. Do you know why? Why does it need a supercomputer? Because at different places people measure the air pressure, humidity, temperature, things like that, and all that makes a grid, and finally there has to be a computation, and the computation obviously takes into account simple hydrodynamic equations. Heat produces convection, makes things go up. As it goes up, and it has to come down because it cannot indefinitely go up. So, there has to be circulating current. So, around the early 60s, 62, 63, that kind of time, when the computers were very primitive, the kind of computer that I was talking about, we had used this printers. So, that kind of computers they were using. In MIT, there was a group working on that, and the person whose name is associated with the set of equations, his name is Lorenz. He simplified the set of equations into this set of 3 equations. Normally, it would be enormously complicated stuff, but that can be simplified by considering, just imagine the whole thing is simplified into this situation, that you consider a ring containing some kind of a fluid, and you have a say a Bunsen burner here, and you heat it up here, and suppose you have got some kind of a cooling device by which you cool the upper part. Okay. So, what will happen? It will tend to go up, and this fellow will tend to go down, but it cannot really go up in both the direction, it cannot go down in both the directions. So, either it will tend to take this route or that route, and these are represented by these 2 different directions of rotation that you see on the computer. So, such a simple thing where the atmospheric circulation has been reduced to this simple annular ring and heating in one spot and cooling in another spot, that can easily be modeled, and he showed that it can be modeled into these 3 simple set of equations, and he was trying to understand how this simple set behaves. Okay. Now, as for any system, for example, many of you are electrical engineers, some of you may be mechanical engineers. For any given system, you will write down the set of differential equations and you will solve them, and ultimately you get a evolution something like this, right. Some kind of a evolution against time. He also got an evolution against time. This will also give an evolution against time. There was nothing very holy about it. But then one day he noticed something queer, because as I told you that those days the computation procedure was not as simple as you have today. So, the computers were slow, the programs were slow, and you had to give those brick size collection of cards and finally that goes into the computer, and then the next day the printouts come out in form of a thick collection of printouts. So, here also I had the same thing, the way I said it, we had to do it in our days. Now, supposing you do some computation for some time and then you want to start the computation all over again, what will you do? So, at the graph were not available to him, it was the numbers that were printed out. So, the numbers at the last column would be entered into the computer and that would go on again. So, if you go for lunch, you enter the another card with those initial conditions and let it run again, and then after the whole day's work you go home, note down the final value, and then next day you come and start all over again. So, that is how it ran really. So, one day he did the same thing, but he noticed he while he went for lunch he entered the final value, and after he came back from lunch he entered the initial value as the final value of the last computation, and it went on. It so happened that that same computation had been done the last day, while it has been done without by ignoring the lunch time, that means it went on. So, he had at the end of the day two computations starting from the same initial condition, but one which had been interrupted at the lunch and one which had not been interrupted at the lunch. But there should not be any difference because the final value was entered by hand, but to his surprise he noticed that after some time it gives for some time the two waveforms were almost the same, and but after some time it was completely different. That was the starting point of what we today understand as sensitive dependence on initial condition. Let us try to understand here. Suppose the two initial conditions for this system, let us make it a little more 26 say, and let us make the two initial conditions, the blue one and the red one, very close to each other. So, can we, probably you cannot read this, but the starting point is 15, 10, 40 for the blue one, and the red one I will make it 15.00001. Chalega? Sufficiently different, right? Sufficiently close. So, we will restart the whole business. Now, where is the red one? Oh, they were going together, that is why you could not see them. Now, you see they have started going two different directions. Okay. You might say that okay 0.0001 is not sufficiently far close to each other. So, let me make happy. Okay. So, let me stop it and let me run all over again. They are moving together, that is why you can say only one. See, they are evolving independently, though you might notice that they evolve independently and therefore, they go in two different directions leading to different predictions about the behavior of the system or state of the system, yet they are more or less their behavior overall is highly predictable, right. They all remain within this range, they move in those two eigen planes, and so you can more or less they are not completely unorderly in the common parlance of the term. Okay. So, what is happening? What is happening is that you have started from arbitrarily close points, and one evolution would be showing something like this, and the other one would be starting at the almost the same point, and it would go on evolving almost the same way if you plot them in time, and finally at some point some deviation will start cropping up, and then after some time you will find that they evolve in a completely different way. This phenomenon is one of the hallmarks of chaos. It is called sensitive dependence on initial condition. And in fact, however close you may go, however close these two initial conditions may go, it will only increase the time for which they more or less follow each other. If you make it 10 to the power minus 12, that kind of close to each other, then it will only go together for a longer length of time, but after some time they will go in separate directions. There exists no separation which will make the two evolutions the same. What is the physical import of this? The physical import took a very long time to sink in the scientific community, and since you are born you are learning this subject some 25 years after this event, we are better placed to give you some idea about what is happening. But it took a very long time for people to really realize what the hell is happening here. See, the point is that throughout human history we have done this business of starting from an initial condition and trying to predict what will be the behavior of anything later. The whole business of classical mechanics is essentially this. What Newton did was essentially this. What all the physicists after him did was essentially this, trying to observe the objects in the sky like the Mars, like the moon, take the reading of the initial condition, write down the system equations and solve it. And that is how they finally were able to predict where these bodies will go. And they were successful. And you see, in the engineering community we do the same thing. When we try design a circuit, when we design a system, when we design a mechanical apparatus, then we do the simulation, means we write down the differential equations, we set it up with a initial condition and we see how it behaves, and we have confidence on that, right. We have confidence on that means if we can predict that it will go from here to here in the state space, it really does go from here to here. Okay. What creates this confidence? It is this. Now look at it from a different point of view. Suppose you have measured the initial condition to be here in the state space, okay, a point. For all practical purposes, is it really a point? No, because supposing you are measuring the position and the momentum of a pendulum, can you measure to the accuracy so that you can state that it is a point? You can never do that. In fact, astronomical observations on the basis of which most of the predictions are based, they are even more inaccurate. So there will always be some inaccuracy in the specification of the position and the momentum, the variables in the state space, and therefore you cannot really say that this is really a point. All you can say is that I have measured it to this value, but I know how much my error bounds are. Normally a proper scientific measurement will always specify that this is my error bound, this is the accuracy of my instrument, and therefore I know that I have predicted, I have measured this value, but I know that it could be erroneous to this extent, but not more. So one would say that here there is a error bar, along this axis there is an error bar. So for all possible scientific statements, one would say that the initial condition is somewhere in this error ball. Okay. So when you actually do the computation, try to try to predict what will be the state of the system, say sometime later, 1 hour later, what are you doing? You are actually evolving from this initial condition to another state, all right. But you can also apply this to all the initial conditions within this error ball. If you do that, then the error ball will change in shape. Error ball will change in shape when it reaches here. Okay. Suppose it has become this much, which means that it has evolved somewhat like this. A bigger error ball has become a smaller error ball. Then even though the initial estimate of the initial condition was inaccurate, you can say with reasonable confidence that the final prediction is accurate. Okay. So initial error actually is shrinking as you are going on the prediction process. The character of the system, character of the vector field is such that your final prediction still becomes quite accurate, and it becomes somewhat insensitive of the error in the initial measurement. Clear? Till the 1960s, people had encountered or studied this kind of systems in the main. What is the character of the system? That the initial conditions, the error ball containing the initial conditions, that shrinks as the system evolves. Now you might again make a measurement here, and then the measurement here would have the same kind of accuracy as here. So you will get an error ball again like this. So you notice that having measured the initial condition earlier and having predicted is more accurate than the measurement now. Okay. If that is true, then our predictions are accurate, reasonably accurate. In fact, our predictions are accurate. That can be how accurate they are, how successful is the Newtonian program. This is a result of the Newtonian program. His program was that I will write down the differential equations, I will set out the basic rules that formulate the differential equations. He did that, and finally that equations have to be solved, and finally you get there. See, in 1995 there was a total solar eclipse. Do you remember that? There was a total solar eclipse. About couple of years before that, the scientists had calculated using this program, using the very much the Newtonian program, had calculated and predicted that the totality line will pass through this particular zone, and the totality belt will be this big, and if you stand at a particular point of time, from this time to that time, you will be able to see the total solar eclipse based on this program, having observed the position of the sun, moon and earth earlier, and having predicted by writing them the system equations, solving the system equation, they had predicted. And how accurate that were? We stood at a point, we watched our clock, we had to synchronize it with the Greenwich clock, all right, but nevertheless we kept watch. It started exactly at the time, it ended exactly at the time. Not only that, in order to make that prediction in future even more accurate, this scientists will have to now observe it properly, right. So Professor J.V. Narlikar had a program in which he stationed school students along the fringe of the totality belt, asking them to note at what time it started, at what time it ended, and that information were again put together in one place to again correct the prediction for the next one. This is how the Newtonian program works, and it worked. It worked with that kind of accuracy. Now we know that is because of this particular property that you can do the predictions. you can shoot and you can finally find out where it will land because of this property. Now, why is this happening? Because now you can easily understand in terms of the character of the system. Here, if you are observing at that point, you can at this point locally linearize the system equations, you can obtain the eigenvalues, and if the eigenvalues were real and negative, then what do we expect? Any deviation from here along this direction will shrink, along the other direction will also shrink, and therefore this ball, which may have started as a circle, will take the shape of an ellipse, will take the shape of an ellipse, but the major and the minor axis both having shrunk because the eigenvalues were negative. Okay. So, as it evolves, the circle evolves into an ellipse, but in both the direction it will have shrunk. So, this rendering is not really correct, it will be something like this. So, this is one related to one eigen direction, the minor axis is also related to another eigen direction, and in both directions they shrink. So, if the system is stable, then you have this property. Okay. If the system is unstable, in engineering you do come across unstable systems, don't you? There the eigenvalues are in the right hand side. If the eigenvalues in the right hand side, it will expand, but it will expand to infinity. Okay. So, it is as if the initial condition, the error ball of the initial condition, that is expanding, 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 and finally going to infinity. That is what unstable system is. So, these are the two types of systems that we had encountered so far. The systems that we see around us, which are stable, have this property that in all the directions they shrink, and if they are unstable, they expand and expand and go to infinity. We learned how to keep instability within bounds, how to stabilize the system. That is the whole gamut of control theory. Just one concept: if you have the starting a set of initial condition as the error ball, a circle, then it will take the shape of an ellipse if the eigenvalues are real. If they are complex, if they are complex conjugate with say negative real part, the orbits will be the spiral, but inward spiral, as a result of which these set of initial conditions will shrink, all right, but it will rotate, it will still remain a circle, but the initial condition that was say here, it will rotate, it will remain a circle, smaller circle, but it will rotate and will come somewhere here. Okay. Are the concepts understood? See, I am not really solving an equation now. I was so far trying to convey the ideas about how we can relate dynamics with the eigenvalues or eigenvectors, and at the end of the day you should be able to visualize that. A situation with real eigenvalues will mean that a ball of initial condition will shrink, but will take the shape of an ellipse. A ball of a complex conjugate eigenvalues would mean that the ball of initial condition will rotate as it goes on, it will rotate, but depending on the real part it will either shrink or expand. Okay. There are two possibilities, it may shrink, it may expand. Okay.
So, but when we are measuring in the present time, then we are expecting an error ball there also.
Yes.
So, aren't we underestimating the error now to predict?
So, his question is that if you are measuring somewhere here and had obtained the error ball and you predict using the set of differential equation and say it becomes this much, and now you observe it, you still have the error ball this much. See, we are making the assumption that from here to here the time is not so large that the technology has improved, so that you can measure the error with a larger accuracy, a smaller error ball. I am not assuming that, I am assuming that the technology is more or less the same. So that if you observe now, you will have some error ball, if you observe it now, you will have some same size of error ball. But the character of the system is such that if you write down the differential equations and start from all the initial conditions here, they will end up here. So even though you do not know where it is in the initial condition, here you can predict with confidence that it should be in this small ball at this point. In that sense, we are not really underestimating the errors. It is the character of the system that prediction becomes more accurate than observation now. That is the character of all stable systems. While studying control theory, we did not realize this, but this is true. This is true, that this is true for all stable systems, stable dynamical systems. So we have a situation where we have come across a system in which there is sensitive dependence on initial condition. We have just seen that in front of your eyes. Sensitive dependence on initial condition means that two initial conditions within this error ball will go apart as the time flies. Obviously, it cannot be like this. Okay. If it is unstable, then what will happen? It will go to infinity. It does not go to infinity, it remains bounded. So now we can specify the character of a chaotic system. Chaotic system means bounded aperiodic behavior. It is not periodic, it is not this, the same state is not coming back, it is not periodic, same state is not coming back, yet there is sensitive dependence on initial condition. So three essential properties of chaos: bounded, aperiodic, with sensitive dependence on initial condition. Just saying it bounded will not serve the purpose, because a equilibrium point, source type sink type equilibrium point is also bounded. Aperiodic will not serve the purpose. Why? I will come to that later, because there are orbits which are bounded, aperiodic, but there is no sensitive dependence on initial condition. So all these conditions satisfied, it is a chaotic orbit. Okay, now let us see how this condition can happen, which means somehow you have started from this initial condition and it is taking, can it take the shape like this in the chaotic system? Obviously not, because if it takes the shape, as it goes on increasing and finally it will go to infinity. That is not possible, that is not the character of this system. So this is not true. Is it possible to have it like this? That means it takes the shape of an ellipse. It takes the shape of an ellipse. If it takes the shape of an ellipse, then the major axis might keep on increasing and go to infinity. But still we will try to do something about it. Can it be like this, that it becomes smaller and only turns, as would happen for complex conjugate eigenvalues? No, because in that case it will shrink to 0. It will shrink to 0. So this is also out of question. So something is happening like this, but then we still do not have the answer. How can that remain bounded? It will inevitably go to infinity after some time. What happens is a trick. If it takes a longish shape, then after some time this can also bend, can't it? and then this will keep on increasing, which means that it will again take this shape, and this whole fellow can bend. Huh? Do you understand what I mean? That means this fellow, when it's bent, how will it look? It will look like something like this. No? I mean, if you take this, stretch it and bend it, it will take this kind of shape. What happens, the interesting thing that happens in a chaotic system is that this process goes on and on ad infinitum. A good metaphor is good. Have you ever seen your mother making paratha? So he would roll the duff and then fold it. Again the whole thing is rolled and again folded. Why does she do that? Because in that case there are in the folds oil would go in, and that makes it very tasty, right? But this is what is happening in a chaotic system. It is stressed and folded, stressed and folded, stressed and folded. So the state space of a chaotic system is a serial process in which the state space is stressed and folded, stressed and folded, stressed and folded. So that process goes on. In fact, this is clearly illustrated by a process that was proposed as a mathematical iteration procedure by Steve Smale. This is the same Smale who got the Field Medal for his work on other areas also. He is a great mathematician. He said, okay, let us start from a square. I will define a process of iteration with this square, and the way that topologies work, that I will do all sorts of processes with it without tearing it. So we will hold it like this and we stretch it. So in the first process he will stretch it, which means that this will become longish, but this side it will shrink. Okay. In the next process he will take it and bend it like a horseshoe. So it will take the shape like this. Fine. Now this is a new shape which can be again taken as a starting process for the point for this process. So this shape will again be stretched and folded. Try to understand what will happen in the next iteration. This fellow will be stretched like this, but now it will be even thinner. Now this fellow will be taken and folded back. All right. Can you now visualize what the hell is happening? This fellow. So we will start with this. This fellow has gone here, so it will go like this here. Okay. Then this, no, it will go like this. This is one bend, and all right. If it is bent like this, it will take the shape. So stretching, folding, stretching, folding. Again put this here, do this process, do this ad infinitum. What do you have? These will be infinitely thin but infinitely layered structure, but will have the property that two initial conditions in these two in this direction will keep on separating out, their distance will keep on increasing, there will be sensitive dependence on initial condition without ever running into the situation that it has to run to infinity, still it remains bounded. Okay. So, this is called the Smell horseshoe mapping, a process by which we can understand what goes on in the state space of chaotic systems. Smell horseshoe mapping. Mapping means that this maps to this through this process. Again, this is continued as a iterative procedure. Ultimately, you will end up with this infinitely layered structure that we see in the state space of chaotic systems. There is another immediate conclusion that in order for this kind of behavior to happen, what is the character of the equilibrium point? If there is equilibrium point in the system, what is the character of this equilibrium point? It has to stretch. Stretch means there should be one direction in which it is shrinking, another direction it is increasing. Shrinking means a negative eigenvalue, increasing means a positive eigenvalue, e to the power lambda t should be positive, and therefore there should be some saddle fellow sitting here. Okay. It has the character of a saddle. So, a saddle equilibrium point must be responsible for this kind of a behavior. In such systems, there would normally be at least one saddle equilibrium point. Okay. Fine. Now, we have more or less understood, have we understood what chaos is? This word is actually somewhat of a misnomer. This word was coined by Jim York. He wrote a paper. The title of the paper is very provocatively titled paper, I should say. We have seen that period 1 system can be there, period 2 system can be there, and he proved mathematically that if a system allows period 3 behavior, means that it also allows chaotic behavior. So, that was his claim. But then this is the first time that the word chaos was used, and since the word chaos is used in common parlance more often in IIT hostels than elsewhere, that is why it is it generally takes a meaning in our heads, but here it has a completely scientific connotation. The scientific connotation is that it is that kind of a behavior of a dynamical system where the behavior is bounded, sensitively dependent on initial condition, and at the same time it is not periodic. Okay. Look at it from another point of view, that you can have a periodic orbit, period 1 orbit, you can have a period 2 orbit that we have already talked about, you can have a period 3 orbit, you can have a period many orbits, and you can also have a period infinity orbit. So, this is nothing but that period infinity orbit bounded. So, that is the character of chaos. Clear? So, what is the implication of the sensitive dependence on initial condition? The implication is that prediction fails. Prediction fails. because if you want to predict, what is the tool? The tool is that you first get hold on the initial condition, plug it into the system of differential equation and predict. The solution of the system of differential equation is your prediction. If there is sensitive dependence on initial condition, even if the initial condition is having very minuscule error, it will lead to completely different final result, and therefore prediction will be completely useless. And that is why after this fellow Lorenz work, it is now more or less understood that weather prediction is pretty much useless. And that is actually why today it is raining and none of you are wearing any protective garment to protect you against rain. There was no prediction. But still, why do these guys use supercomputers to try to predict? If it is true mathematically that prediction is pretty much useless in such systems, why do these guys spend millions of rupees on buying supercomputers and trying to do something about it? It is because if you have the two actually did follow each other for some time, which means that prediction is good within a certain time frame. Okay. Weather prediction therefore is not infinitely good. You cannot really keep on predicting the weather, but you can predict within a day or two, and that is exactly what they try to achieve.
So, what if the error is very small?
Or if the error is very small? Good point. Means that if say this error ball is evolving into an ellipse, but then doing all sorts of things that I just discussed, but the rate at which this direction expands is not very large. That is what you mean? Now this is related by what? You can see that this expansion of this line into that line is the result of e to the power lambda t with lambda positive. Okay. So if we can measure this lambda, we can sort of specify the rate of expansion. Okay. And your point is correct, that the extent to which prediction will be good will depend on that lambda. But this is a nonlinear system, so you cannot measure lambda everywhere. We learned how to measure lambda, we learned how to measure the eigenvalue at the equilibrium points, and these are not happening at the equilibrium points. This is just evolving. So what do you do about it? You could, for all practical purposes, keep on following that orbit. Suppose you do what I did, just calculated the orbit, and for every point you keep on obtaining the Jacobian and calculate the eigenvalues. Take the average. Good. That is a reasonable estimate of the rate of expansion, and if that is not very large to the positive side, a small positive number maybe, then you would say that okay, even if I know that system is chaotic, I can still predict to say this many days with confidence. Therefore, following your lead, I can tell that the measurement of this rate of expansion is of vital importance when it comes to deciding whether I can predict or not, or to what time frame I can predict with confidence. This is a very important number. In the next class, we will take up the issue of how to measure this number. How to measure this number. Notice that it has the character of the eigenvalue, but it is not really the eigenvalue, in the sense that the system is nonlinear system. Eigenvalues can be computed at every point, but here we are talking about the average eigenvalue, average positive eigenvalue. So that is not really the eigenvalue, it is sort of a eigenvalue averaged over the orbit, not just everywhere in the state space. As the orbit goes, I am calculating the eigenvalue everywhere and then averaging out, averaging the positive one out, and you are getting a number. These numbers which have the character of the eigenvalues, but related to the nonlinear system are called the Lyapunov exponents. Obviously, in a 3-dimensional system there will be 3 Lyapunov exponents. Out of that, if one is positive, I would say that there is sensitive dependence on initial condition. So, one of the conditions of chaos is that at least one Lyapunov exponents must be positive. Fine, that is all for today. We will continue with in the next class.